Hello and welcome to my video on the Nintendo Game Boy Advance. Going into 256 colour tiles this time. So I'm going to assume that you've seen the last video on the 16 colour tiles, as lots of the theory behind it is still relevant here. So we'll jump straight in again. So just like in the 16 colour tile video, we have the modes that the Game Boy Advance supports. So 6 different modes, all the tiles still 8x8 pixels in size. The tiles are arranged on tile maps, which are configured like a grid. So if I come to here, you can imagine this is our example of a tile map here. So these are the tiles here laid out in a grid fashion. So this tile here would be top left, this tile here would be bottom right. That's how they are arranged in a tile map. So get back in. So the tile maps can be either 32 by 32, 32 by 64, 64 by 32 or 64 by 64. So the same stuff is relevant here using 256 colour tiles. So the demo I'll be presenting will be using mode 1, which is the main one that you would use really for doing tiled graphics. So the key sort of takeaways really is that we have 4 background layers in mode 1 that we'll be working with. Each background layer can be either set to use 16 colour tiles or 256 colour tiles, so you can mix and match different layers to use different tile types. However, there is only a total of 256 colours in the Game Boy Advance's colour palette for background tiles. So if you mix and match different tile types, then you will need to make sure the colours are laid out in such a fashion that they work fine with all layers. It's kind of what you even just using 256 colour tiles alone, you still need to kind of arrange the colour palette when working with tiles, as although you can have a lot more colours in one tile at a time, you might want to have certain blocks of those colours pegged for one sort of background type or asset type. So you still end up to some degree arranging the colours in blocks of 16 anyway. So the working with tiles, we have 2 types of structures that we need to use. We have a tile map, which is how the tiles will be arranged on screen, and then we also have tile sets, or character blocks as they're referred to in Tonk lib, which is the library which is underneath all of the code that I use for my programs on the Game Boy Advance. So each background layer can either share its tile set with another layer or individually have its own tile set. However, they all must have their own tile maps. We have a limited amount of video RAM that we can use for this. So we need to set up a tile set and a tile map. Now, a tile set is in a block of 16 kilobytes in size, and a tile map is usually 2 kilobytes if the size is 32 by 32. Obviously, if you grow the map, then it kind of doubles in size. So if you've got 32 by 64, that's now 4K. Same with 64 by 32. However, if you're using the 64 by 64 map, then that's now an 8K area to work with. So I'll quickly go across to how you can visualize video RAM here. So we've got 96K of video RAM that we need to arrange all of our tile data into. So as you can see here, we've got the top area of video RAM is kind of set aside really just for working with background tiles, and then the bottom part of the video RAM is where you would work with your sprite graphics. So this is arranged here showing tile maps in this area here, so these things will overlap in our video RAM area, so you need to work out where they would need to be so that they can coexist in video RAM and not overlap and destroy the contents of one another. So we end up with 4 potential tile set areas we can use for our background tiles, and then we have 32 locations for tile maps if they're obviously 2K in size. Now when you work with 256 color tiles, it reduces how many tiles you can actually have in a tile set. So when we are working with 16 color tiles, we can have a total of 512 tiles in one tile set. However, when we work with 256 color tiles, that is double. Each tile in 256 color mode takes up 64 bytes, whereas in 16 color mode, each tile only takes up 32. So we half the amount of tiles that we can use in any tile set when we're in 256 color mode in one of the background layers. So when we are in 256 color tile mode, we obviously don't have to worry about setting a palette to use, as that bit is now no longer used. So the entries in a tile map, these numbers here, these are 16-bit numbers. This here, this little thing here, this lays out the bit flags which make up one of these numbers in the tile map. So you'll see here we have 10 bits set aside for the tile ID in the tile set, which is used with that background layer. And then we have a horizontal bit and a vertical bit flag, and then we have a number of palette IDs at the end here. Obviously these are not used at all when working with 256 color tiles, and also the tile ID as well. Obviously the upper bits are not used, as you can only have a number between 0 and 255 in here. However, you can still flip the horizontal or the vertical bit flags in here to flip the tile. And then this little diagram bit here just shows how the colors are set up. So you would have whole palette of colours set up for use with the 256 colour tiles. So I'll jump into now how a tile was made up here. So this is our example graphic here. This is our first 8 colours in a palette, and then you'll see here that each pixel in a 256 colour tile is given 1 whole byte, as the range of a byte is between 0 and 255. That obviously maps nicely to the colour palette. So as you can see here, the yellow colour here in our palette is number 1. So wherever we want to set a pixel over there, we just put a 1 in our data array, which would be loaded into video RAM. So it's nice and easy to visualize these. You could even create arrays by hand, really, without the aid of a graphics program, and just type it in. Obviously, the more complex your graphics gets, that would obviously be too much of a pain to actually do. So that's pretty much all I want to talk about here. This goes over all of this. Nothing more to say here, really. So I'll save and close this, and then we'll jump into the demo code, and then I'll also explain a few things about the demo as well. So I'll show you the example code, the example program first. So here's our example here. We've got Super Mario, collect the coins. There is no collision with the scrolling blocks. So you may notice that this appears to be moving smoothly as if it was like a sprite. Now the way we've done this is the Mario tiles are actually on their own background layer, and we are actually scrolling the whole background map, and then the tile blocks here and the coin are on another layer, and our font set is on another layer again. I haven't put any collision in with the backgrounds as I run out of time when coding this demo yesterday. So you've got an example showing how you can collide with the coin. Oh yeah, and you've now gone to implemented level 2 as well. Obviously that scrolls far too fast, so I'll quit that now, and we'll jump into the demo code and I'll talk you through it. Oh yeah, what we'll also do as well first is I'll show you the graphics used here. So this is our wall block here. I'll change the colours for this. And then we have our Super Mario graphics here, which is from a game I'm currently working on in the Super Nintendo. There is no animation. I literally just took the first 12 tiles here from this side, and then we have our coin here as well. I literally just tuck this tile here, and then all of this I put together into one tile set here. So all of these in total here, there's like 34 colours in total here, and then there's a total of 128 tiles. So there's a number of ways you can organize your graphics when working with 256 color mode. One thing you can do is to sort of, if I just open up a text file here. Now, what you would kind of do is maybe you would have your different characters in here, and then you'd say, oh, this character uses 24 colors, and then as you see here, the font has 6 colors, so you might want to record. Okay, so the colors for Mario start at 6, and then you would create like a list of where all of the colors that you're using start and end. So for example, if you wanted to switch the colors for Mario to turn him into Luigi, you would know that you would start at the color or the palette number 6, and then change 24 colors from there onwards. Replace them with like green variants for Luigi if you wanted to do that. Now, one of the things which is hard in 256 color mode is sharing colors between various graphics. Obviously, you have a lot more colors to work with, which means you can create a lot more detailed scenes. However, trying to intermingle graphics to use colors which are already in use can be problematic, especially if you want to do any sort of color scrolling. But definitely record the start number, and then this also allows you to when working with my graphics converter here, if we jump in here, so when in 256 color tile mode here, this window here is the palette start ID. This is what it's used for really. So for our Mario character here, we could put this start as being 6. And then if we look at our graphics here, we'll see that each sort of image here is 32 tiles across by 24 down. So we'll put that in here as well. And then one thing to bear in mind as well is whenever we draw one of these, whatever graphics we create, if our character is to have a transparent color in it, then obviously we do not want to include this color. In this case here, this magenta color here, we do not want that color to be included in our palette. So this is where this option here comes in, where we do not export the first color. That's what this here does. And we also will not be using our image palette at the top left in this case. So we'll select this option here, which will create the palette from the actual image. Now, if I drag that image in from off screen here, it's found 16 colors and it's removed the first one here. So if I save that now, so it's created two, although it says 2 tiles, that's actually 2 32 by 24 blocks. So if I close this now and then we go in and have a look, you'll see here that the if I just bring this back across, arrange the windows here so that I can explain this to you here. So what we need to do here is go into show the pixel grid here. And if we zoom in here, you see the first tile here is all zeros. So because we've not exported the magenta color, it will take color 0 from the normal sort of the full palette, whatever color that is in the 256 color palette, it will revert to color 0 here. And then when it first comes over to here, you'll see here that this is arranged in 8x8 tiles. And then you'll see here that the first brown color here is at the bottom right here, and that's it there. So the first color it's found is this brown color here in tile 3, and you'll see that's these here. So what this allows you to do is to work with like graphic tiles without having to include the full color palette for the whole graphic set. Hopefully that makes sense to you. Basically, when you're working in 256 color mode, that full palette of 256 colors is in theory available to all the graphics. But you might not want them to use certain colors at certain locations. You might want to keep a whole area of colors reserved, if you like, for one graphic. And then that's where these commands come in my graphics converter, to allow you to start the colors at a certain offset in the color palette. Hopefully that makes some sense to you. If not, it probably will in the future when you work with this more. So as there's only a few graphics that I'm using in the demo, I decided to pack them all into the actual font tiles. So as you can see here, they're arranged in a way that's nice and easy for them to actually be drawn. And one nice thing about packing them all together like this is it minimizes duplication of colors, as if you put them all into one sort of tile set like this, then they'll all be reusing colors between the various sort of graphics. So I didn't want to go too heavy in the graphics for this. This was purely to show you how 256 color tiles are actually built, and then how you can work with them. So this is just a quick demo. So there's only one tile set we're working with here. So one thing you could do here is you could have like if you were sort of like had like an end of level boss or something, you could give that one large character one background layer, and then by scrolling it around like I have done in this demo here, we basically what's sort of happening here is the Mario tiles are given their own area, and they're only drawn once as well. There's not a lot of drawing going on here. The tiles for the Mario character are drawn at the start here, so we have a level initialize function, everything's packed into the title screen here, as there's not a lot going on. So the Mario character is assigned to background layer 2, and this is him drawn once. And then all we do is we have a boolean here which just records whether the player has actually pressed any buttons on the D-pad or not. And then we have a rectangle which holds the pixel position of the player. So this rectangle which holds our player's actual pixel location on the screen also holds the width and height of our character for collisions as well, so it doubles up. So you could easily do that with like a big boss, if you like, for a game. And then you'll see here, if we've moved anything here, we also have some code to restrict our player from moving off the screen. Although in theory the character itself is not actually moving, the whole background layer is actually being scrolled. As you can see here, if we move, then we scroll background layer 2 in the opposite X and Y direction to what we are actually moving. So that's how the player is moved there. Now the scrolling the pillars is slightly more complicated. So all of the pillars, they are kind of drawn one by one as they are needed. So we have a variable which holds the scroll speed. I would invite you to have a play around with that. And then in here is kind of how it all sort of works. So we have a variable here called tile update x. As the tiles are 16 pixels wide, when we start off the level we set that to 16, and then we subtract the scroll speed from this variable here. If it reaches 0, then we know it's time to draw another tile. As the screen size on the Game Boy Advance is 240 pixels wide, that gives us a 16 pixel area which is hidden on the actual tile map. So all we do is every 16 pixels moved or scrolled, we draw a new tile to the hidden off-screen area, which is what this is doing here. What we also do here is we generate a random number for the pillar, and this number basically is the height the pillar will be drawn. I'm not going to go too much into all of the code here, but have a play around with it here. So what this tx is here is it works with scroll x. So scroll x is the amount that background layer 1, which is where the tiles are drawn, is scrolled. Here we go here. So background layer 1 is where the coins and the pillars are drawn. What we do each update here is we set background layer 1 to the value of scroll x, and then we increment scroll x by the scroll speed, and then we use a bit mask of 255 on scroll X to make sure it never exceeds that value. So scroll X will only be 0 to 255, as the tile map itself is only 256 pixels in width anyway, so it's literally just like constantly wrapping around. And then you'll see here the tile update X is subtracted from the scroll speed as well. And then, like I said, if the when tile update X equals 0, we draw a new strip, which is basically drawing a new pillar to the screen. That's how that works. So it kind of looks like the sprites, but there are no sprites. As we have 4 background layers to play with, we can put our player onto one. So we even have another layer 3 as well, as I didn't use background layer 3. So you could put something on that as well, or you could shift everything up. So background layer 0 is just used for drawing the amount of coins needed to complete the level, and the score and the level number. We put the coin inside this entity object here, and I was going to put the pillars inside here as well, as the easiest way to work out collisions is to create collision rectangles for the shapes of the objects, and then every time the screen scrolls, you would subtract the scroll speed from the collision rectangle. And then we also need to record the tile position as well, because if we need to erase the graphic, like in the case of the coin, we need to know the tile location it was actually drawn at, because in theory the all the tiles drawn on the tile map, they aren't actually moved at all on the tile map. The tile map is scrolled, but the objects themselves, the tiles, are still in the exact same place they were drawn. So to record where they are in pixel locations, that's where the collision rectangles are used. So it's all fairly straightforward here. This is where the sort of magic happens here. We need to work out in this part here where the hidden area is on the actual tile map. So what we do is we take the scroll X position and we add 240 to it. But what that means is that at the start of the level you have to have scroll X as 0. So we always need to know where the off-screen area is to draw our tiles. So we add 240 to scroll X and store that in our temporary variable tx, which is the tile X position. We then use the value of 240 to mask tx, so it's always within range 0 to 240. We then divide that by 8 to convert that number into tiles. That then gives us where we draw our tiles then, which is what this part here does. So this here is how we calculate where to draw our pillars. We only want to draw 8 pillars, as only 10 of those tiles can actually fit on the height of the Game Boy Advance screen, as it's 160 pixels in height and each tile is 16 pixels in height. So we only want 8, but we want to draw the tiles from the bottom of the screen up, which is what all this does here. So tile start is the top of the pillar. So in this case we subtract this value from 9, which is the bottom tile on the screen. However, this number here is working with blocks of 16, so we have to times that by 2 to convert that to working with our 8x8 tiles. So this is then what we use to calculate where our pillar should start. So when we draw each block here on the screen in the hidden area, you'll see here we go from 0 to 20, as there is obviously 20 tiles in height, and then we go in steps of 2, as each tile is 16 by 16 in size, so 2 tiles in height, if you like. If Y is smaller than the tile start, then we need to clear that tile out. Otherwise we draw the war tile in place. If you don't get what's going on, just have a play around with it all until it makes sense to you. We have a spawn timer that we use for spawning the coin. So the coin will always be sort of drawn in an area above the starting point of the wall. So it will always be above the sort of like pillar wall whenever it's time for a new coin to be spawned. And we only ever spawn one if it's not alive. So we plot the coin on screen, which will be above the wall tile, hidden in the sort of margin, if you like. We then need to record the coin's tile position, which is needed for when we maybe collect the coin. We then set the coin to alive, and then we set the collision rectangle here. So you notice that we always set the X position to 240, because in theory it is always at pixel location 240, which is just off the screen. And then we play a sound effect. I'll get into sounds in another video, so I will not be going into any details on that. And this is pretty much how it all works. I'm not going to go into any more details here. Jump into the code and have a play around. Hopefully this will allow you to get started with 256 colour tiles. All the code here is pretty much built on top of the sort of Game Boy Advance demo code, which I put in the first video. So there's no real additional code in here. This is just showing you how to use 256 colour tiles, and then this stuff here, which this little sort of game demo, if you like. This is just to make it more interesting rather than just show you tiles on their own. So hopefully that you found this interesting and it'll be useful to you, and I will catch you in the next video on sprites. Right, catch you next time.